Alright, so sorry for the delay. The laptop crashed on me while I was booting it about 5 minutes ago, so I'm having to restart. And I'm still kind of in the middle of bringing things up. So I see that there's a question about one of the problems. Could you be a bit more specific as to which one? And also understand there's about a 10-second lag in this video, so whenever you hear me talk, I spoke about 10 seconds ago in my version of the stream. All right. So the question is the molarity of 60.21 grams of ethanol, C2H5OH, dissolved in 0.5236 liters of solution. So we'll start with that problem first. So we have 60.21 grams C2H5OH. And we want to know the molarity of it given that we have 0.5236 liters of solution. So the first thing we're going to need off of this is the atomic weight. So I'm going to Excel up. So we got 2 carbons each of 12 plus 6 hydrogens plus 1 oxygen gives us a weight of 46.0. grams of C2H5OH for every mole. And this will give me 1.308913 moles. So for all intermediate calculations, make sure that you're carrying everything out. You're not going to want to round, you're not going to want to do significant figures until you get to the very end of the problem. Now to figure out the molarity, it's the moles per liter. So we're going to take that number, 1.308913, divide by 0.5236 liters. And I get 2.499834. So now comes the formatting part of the problem. So we have to look over the problem and see how many sig figs we should have reported in the final answer. Now, thing to keep in mind here is that conversion factors do not affect your final significant figures. So we're going to treat this conversion factor here, the 1 mole per gram, as an infinitely precise number. We know it's not, but this is going to be true of all conversion factors. We're just going to have to treat them as infinitely precise. So the only numbers given to us in the problem are the 60.21 and the 0.5236. So there's 4 sig figs on that number, 4 sig figs on that number. So we need to truncate this number to 4 significant figures. So if we round that 8 up, we get 2.500 molar. And that ends up being the answer we had to put in. Now if you put 2.5 in, that's only got 2 sig figs in it. And if you put 2.50, that's only got 3 sig figs on it. We know this number to this degree of precision. We know it's 2.500. It's not 2.51 and not 2.49. So that would be the answer to that question. In terms of the molarity of 60.21 grams of ethanol dissolved in 0.5236 liters, the answer is 2.500 molar. So the next question, osmotic pressure of a 1 molar solution of sodium chloride. and I'll write the deal. Oh. So we have a 1.00 molar NaCl solution, and we're at 25 degrees C, and R here is 8.314 kPa, liters mole Kelvin, and I here is 1.90. So define the osmotic pressure. I equals trim. So the temperature here, it's 25, but it needs to be in Kelvin. And the tip-off that this needs to be in Kelvin is that you've got the gas constant R. So R always has units of Kelvin in it. So we need 298 Kelvin. Don't do the 273.15, like that 0.15 does not buy you much. So you got 298 times 8.314 times 1.90 times 1.00. And when I multiply that all out, times 1 times 8.34, I get 4707.387. So again, we're going to have to kind of go back to sig figs here. Based on the numbers I'm seeing on the screen, I'm guessing this is what the problem gave you. Concentration, the temperature here are to 3 significant figures. R here is a gas constant. I is also considered just a physical constant. It doesn't have sig figs associated with it. So your final answer needs to be to 3 sig figs. So you get 4,710 kPa for that number. So next question up. Freezing point change if we have a 0.1 molar HCl solution. All right, and actually let me go back to this osmotic pressure question really quick. So for the osmotic pressure question, I see where your mistake is actually. So I'll share the screen with you really quick. So the solution here is 0.1 molar, it's not 1 molar. So instead of getting 4,710, you would actually get 470.1, and that would round to 471. Now, technically this 0 here is wrong for sig figs. That's only 3 sig figs, which is why the key expects will accept 470.1 or 471 or 472. But that looks like the mistake is actually it's not 1 molar, it's 0.1 molar for that problem. Okay, freezing point question. We have a 0.1 molar, or mole, HCl in water, and we want to find the freezing point. So the thing we're going to need for the freezing point, you can find this in books, you can find this online. If you're looking for a rapid place to access this, and you'll see this when you go to take your test, that there's a sheet that you can just download that will give you the same information just to save you the trouble. On those study packs, there's a table of KF and KV. These are just taken from the book. They're just meant to kind of condense the information to one place, but again, you would find this information if you Googled it, if you looked on the book, it's all going to be there. But we're looking at water and we want to figure out the change in the freezing point. So we need this 1.86. Got us to disregard the question, but for those who are curious how you work it, I'm still going to work it. So we get delta T equals K I M. So we have 1.86. For HCl, the Van 't Hoff factor is 1.9, and the molality here is 0.1. So if we plug it all in, the full answer here, 0.03534. Yeah, because it's 1.9. My mistake. .3534. This is the only thing you're given that is not a physical constant. So we're just going to stick to 3 sig figs in our final answer. So your final answer here is going to be 0.353 degrees C or degree Kelvin. All right. So next question I'm getting is about theoretical packing density. So let me bring that up in the PowerPoints really quick. This is going to take me just a minute to find where these formulas are. Not that one. All right, got it up. So theoretical packing density of boromirium, if atomic weight here is 35.3 grams per mole, and the atomic radius here 0.131 nanometers, and we have an FCC crystal, so a face-centered cubic crystal. If you go to the lecture notes online, this is also kind of in your book, but this is going to be a bit more efficient way to find it. It's underneath the first lecture, Colligative Properties. Let me bring it up on the desktop for you. These 3 formulas are actually given to you. They'll also be given to you on the exam, plus you have access to the notes anyway. So for an FCC crystal, the packing density is 4 over 8 times the radius squared to the 3/2 power. There is a conversion factor between nanometers and centimeters, so it's 10 to the 7 centimeters over nanometers over 1 centimeter to the cubic power times the molecular weight, in this case 35.3, all divided by Na, which is Avogadro's number, which is 6.02 times 10 to the 23rd. So what I'm going to do is I'm going to pop this out in Excel really quick. Biggest mistake I see with these types of problems is just entering it into the calculator more than anything else. So just kind of litter this with parentheses. So the first part of the formula is 4 divided by 8 times the radius squared, which is 0.131. The whole thing raised to the 3/2 power times 10 to the 7th raised to the 3rd power times the molecular weight, which is 35.3 divided by Avogadro's number, which is 6.02 e to the 23rd. This will give you a packing density of 4.61. Again, go off the sig figs given to you in the problem. There's 3 in the atomic radius, there's 3 in the molecular weight. So your final answer here is going to be 4.61. Next question, determine the total vapor pressure of a 10% mole acetone solution with a 90% mole ethanol solution. We are going to make the assumption of ideal solutions, and ideal solutions will allow us to use Raoult's law. And what Raoult's law says is that the vapor pressure of any mixture is just a linear combination of their vapor pressures multiplied by the percentage that's in the vapor phase. So again, if you go back to those tables and those class packets, it's going to kind of give you a condensed version of all this information, but all this information is available online. So for acetone, the vapor pressure is 30.8 kPa. And the other component here is ethanol. And its vapor pressure, 7.87. So the total vapor pressure is each mole fraction times the vapor pressure, Xi times Vi, and it's going to be the sum. Now, the thing to keep in mind here is that it should make sense to you. So let's say I had a mixture that was 100% acetone. It should have a vapor pressure of 30.8 kPa. So if I say X is 100 times 30.8, that would mean a pure mixture of acetone would have a vapor pressure of 3080 kPa. So the mole fractions here are not in percents, they're actually in just normal integers. So for the acetone component, it's 10% acetone, so it's going to be 0.1 times 30.8. And for our ethanol contribution, it's the 0.9 times the 7.87. So I'm going to carry out that calculation really quick. 0.1 times 30.8 plus 0.9 times 7.87. Your final answer is going to be 10.163. Everything is given to you in the problem in terms, I'm assuming in 3 sig figs, but your final answer here needs to be reported to the correct number of significant figures. So if it says 10.0%, you would report it as 10.2. If it said just 10 point, it would be 10. If it said 10.00, it'd be 10.16 for the final pressure. All right, next question. Can you do a molality to weight fraction problem? Let me bring one of those up. Okay, so while I write this up on the board, I'll share my screen with you. So this will be the first homework problem for that concentration's hard. So the first question is asking, what is the if the molality of an Na plus solution is 3.90 mole Na plus, what is the weight fraction? And ultimately we're going to get an answer of 0.823-ish in that range. Now, just as kind of a guiding light here, molality and molarity, little m and big M, are roughly the same number, particularly if the concentration is less than 0.1 molar or 0.1 molal. So your final answer, if we were to go from molality to molarity, those should be roughly the same number. Your weight fractions here are generally 10 to 100 times smaller than the molarity and the molality. So if you're curious if your answer makes sense, your molarity and your molality should be about 10 to 100 times larger than your weight fraction. And when you go the reverse way, your weight fraction should be about 10 to 100th as big as your starting molality. So in terms of how you actually work these types of problems, there's a few steps you want to use. First step is that you need to write out the units of what you're given. So we're given molality. The units of molality are moles of solute per kilogram of solvent. The second, you need to write out the units of what you want to get to. So we want to get to weight fraction here, and this is going to be grams of solvent or solute over grams of solution. Third step, based on the starting units you're given, you're going to assume you have one of whatever is in the denominator. So in the case of molality, we've got a kilogram of solvent, so we're going to assume 1 kilogram of solvent. Now, this is not the same assumption you make every time, and I see this mistake made a lot. It depends on what you're given. If you're given molarity, the units there are moles per liter of solution, so you're going to assume 1 liter of solution. If you're given weight fraction, that's grams of solute per grams of solution, so you would assume 1 gram of solution. The assumption you make is based on the starting concentration you're given. Now, the game we're going to play here is that concentration does not depend on how much you have. So if we assume we have one of whatever's in the denominator, that's not going to change the concentration. Now, how do we use this? There's 3 formulas. The first is that the moles of solute times the molecular weight of the solute equals the grams of solute. Second, the grams of solution equals the grams of solute plus the grams of solvent. And finally, the density of the solution is equal to the grams of solution divided by the volume of the solution in liters. So, we have assumed we have 1 kilogram of solvent. This number is here. Because we have 1 kilogram of solvent, if we multiply the molality by this 1 kilogram, that would give us 3.9 moles of Na+. So based off our assumption, if we use this assumption, we'll also, because of the assumption, we have 3.90 moles of sodium. So that gives us that number there. So if we had 3.9 moles of sodium, that would give us, let me work it out, (89.7) grams of solute. That we can stick into that formula, so we have 89.7 grams of solute. We have 1 kilogram or 1,000 grams of solvent, so this gives us 1,089.7. Wait, I think sodium's 23.1. No, it's 23. So that would give us 1,089.7 grams of solution. We use these formulas to figure out that based on this assumption, how much of this do we have? So if we have a kilogram of solvent, we have 1,089.7 grams of solution and 89.7 grams of solute. And if we put those numbers in, based on our assumption, we'll recover that 0.0823 grams per gram. So the next question down. I had a question about the discussion board. The new one that was posted is due tomorrow or next Thursday for attendance. So the discussion boards are due Tuesdays and Thursdays. So the one that just appeared today, because yesterday's due date has changed, you have from today until tomorrow, technically, for the due date. That said, I'm going to check Monday to see which ones were done. So technically you have through the weekend to do the ones for Thursday. Again, the due dates are more to make sure that you're progressing along in terms of the content of the course. You do need to do them, so if you're thinking you're just going to wait 2 or 3 weeks to do them, one, it's not going to do you any good. But I am going to kind of give you that grace that I'm probably not going to really put in the attendance until next week anyway. So if you need to wait until Friday or Saturday to do the Thursday discussion board, that's fine. Just make sure you do it before Monday so you're counted as present in the course. So next question now. How do you find the mass fraction of a solution given molarity and density? This is a bit more involved, but it's still going to follow this same line of reasoning. So here the problem is a 0.2 0.2500 mole lithium, let's see here, lithium chloride solution. And we're given that the density here is 1.020. Now, both of these are 4 significant figures, so your final answer here is going to need 4 significant figures. It should say 11:59 on the due date. And the 11:59 is basically what Blackboard does for like midnight due dates. Anyway, back to this problem. So we're given molarity. Units of molarity are moles of solute per liter of solution. And we want to get to weight fraction, which is grams of solute per grams of solution. So these are the 2 numbers we need to calculate the weight fraction. So we've got grams of solution here, and we've got grams of solute here. We've also got grams of solution here. Because we are given molarity, we are going to assume 1 liter of solution. Because we have 1 liter of solution, if we multiply the molarity by that volume, we're going to get 0.250 moles of LiCl. So these are our assumptions. We have 1 liter of solution, which will go into our volume of solution. And because of this assumption, we're going to get 0.250 moles of solute. Now, what we need are grams of solute, and we need the grams of solution. So we actually have these 2 formulas we can work with. So to convert our moles of solute to grams of solution, grams of solute, we just take our 0.25 and multiply by the molecular weight of lithium chloride, which is going to be the 6.9 plus 35.5. What I'm getting is 10.6. Density here is 1.020. I assumed a liter of solution, but the density here is in grams per milliliter, so I have 1,000 mLs of solution. So the mass of my solution here is 1,020. So now I can just plug these in. Based on this assumption, I would have 10.6 grams of solute and 1,020 grams of solution. When you work that out, your weight fraction here, 0.01039. You're going to want to carry it to 4 significant figures because each of these had 4 sig figs in them. It should be saying 10:59 p.m. It should be saying that it's due at midnight. But let me take a quick look at that because that's easy to fix on my end. But definitely when I checked today, it was still showing that it was due. Okay, let's check the WebAssign. How weird. Yeah, you're right. It does say that. Why does it say that? Because it doesn't say that. Okay, hold on. We can easily fix that. Apparently when I grant the extension, it thought 11:59 and not, it put 12:59 in. So that's Easy to fix. So now if you go back to WebAssign, it should be showing you 11:59 p.m. tonight. You are correct. The due date should all be at midnight, but it's showing... Okay, that's just plain weird. I'm going to fix these all while I'm here. Give me just a minute to fix all the due dates. Shouldn't take me but another minute. No, this was set up so this way they would all be due at midnight to make it easier on y'all. Almost done. Yeah, it's weird. I know I set these up for 11:59 p.m. when I set this course up. Yeah, if you ever see anything weird with the due dates, let me know. Um, you're gonna find that just every now and then something just doesn't get loaded right. It happens. Particularly when Blackboard and WebAssign do some weird migrations. Sometimes they mess with our dates. But yeah, if you ever see a weird date, let me know. Like if it says like 2 o'clock in the afternoon or like 11 o'clock in the morning, these are all meant to be due at midnight just so you have the full day to do it. But yeah, thank you for catching that for me. On my end, I mean, if you're curious what it looks like on my end, this is what Blackboard looks like for us. Or WebAssign looks like for us. So yeah, sometimes we just lose the details. Now, something I have commented on in a few emails, just so y'all know, I keep the homework intentionally at low values. And the big reason for that is that even as a student, like when it's 15%, I totally understand you want to get 100% because that's a huge chunk of your grade. I either do the 2.5% because I'd much rather you focus on understanding the concept. So you're going to find one like we have a redox homework at the end of the semester. It's involved, but if you try to hyper focus on getting the right, like getting a perfect score, you tend to lose the details on like the concepts. You become more focused on getting an A and less focused on getting the concept. So with the homeworks, just feel free to like, if you don't get 100%, that's fine. If you do absolutely no homework this semester, the worst it's going to do is take 2.5 points off your final grade. So as long as you're doing the homework, it's not going to substantially affect your grade. So in terms of using the Vant Hoff factor, do we use 1.9 or 1? So I need to clarify this in the notes, and I'm going to clarify it in the next edition. Use 1 if you don't have any other information. It's a bad assumption, but sometimes it's what you're given. In general, we're going to focus on problems where they're given in tables. So particularly with that worksheet online, those extra practice problems, go off those tables. They do exist. This more comes up because you're going to be working with, if you work with any type of if you work with an organic compound dissolved in organic solvent, which you typically do for the lab, that's when I ends up being 1.00. But again, you need to stick to using Vant Hoff factors if they're available. For my homework problems and for my test problems, they are available. It's a conversion factor, 1.9 versus 2. So Vant Hoff, so there's a difference between science and engineering. Science actually has a theoretical basis. Engineers are more kind of, if it works, it works. We don't really care where the numbers come from. So the Vant Hoff factor theoretically should be the number of ions a material breaks into divided by the number of parent molecules. So for something like HCl, it should be 2. So why does HCl not really break into 2 molecules? Well, water is composed of H plus and OH minus. So even though it breaks into 2 molecules, one of those has a positive charge, one has a negative, and so the ions in water coordinate to them. So really, even though it breaks into 2 ions, we have to account for the fact that those ions attract other ions, which in principle removes the ions from solution. So long story short, we have to use the tables because the theoretical is almost always wrong. And you'll see this with FeCl3. FeCl3 has a Vant Hoff factor of like 2.7. So how do you find molarity from a given freezing point of compression, Vant Hoff factor, the solvent's name, mass of solvent, mass of solute? So for the you would use this more for, hold on, clear up some space. So to find the molality from a given freezing point depression, Vant Hoff factor, solvents names, and all that, you would just rearrange the formula. So we have delta T equals K I M. So to find the molality is just your given delta T divided by K times I. So if you're given the freezing point to temp change, you're given the Vant Hoff factor, and you're given I, you'll get a numerical value for the molality. So it's just rearranging that delta T equation. Now, if you're given the mass of solvent and the mass of solute, what you're really probably being asked to find is the molecular weight of the compound. So to do this, we recognize that molality is moles of solute over kilograms of solvent. So this whole chunk comes from this formula. This is just the definition of molality. Now, the other relationship we have is that moles of solute times the molecular weight equals the grams of solute. So our moles of solute equals our grams of solute divided by the molecular weight. And we can further substitute this into this problem to give us grams of solute over the molecular weight times the kilograms of solvent equals this delta T over KIM. Now, personally, I think it's better if you break this into smaller chunks. So let's solve for the molality first. So Julie's posted a problem here. If our delta T is 5.81, our constant here is 1.86, I is probably going to be 1, and the mass of solute equals 3.13 grams. The mass of solvent is Oh, I'm guessing you saw for the molality. Oh, you got 10 grams. That makes a lot more sense. And the mass of the solvent is 0.1 kilograms. So let me rewrite this to simplify it. So you got the delta T equals K I M. Delta T is 5.86. KF is 1.86. I is 1. So if we solve for molality, how do you find the temperature change? Well, it's given to you. The delta T is the temperature change, that 5.81 degrees. So the delta T, delta means change. So that delta T reflects the change in the original freezing or melting point minus the old freezing or melting point. Typically I don't worry so much about making a report what the new temperature is, simply because it gets kind of complicated. You start losing a lot of, in my opinion, you start losing a lot of details. The delta T, if it's a boiling point, you would add the delta T. If it's a freezing point, you subtract it. In terms of an example, we're going to work joules right now. So the 5.81, sorry, 5.81, not 5.86. That's easy to fix. So this will give us a molality of 3.13656, and we're just going to kind of keep everything out there. Now, molality is equal to the moles over the kilograms of solvent. So we're given the kilograms of solvent. So if we rearrange, we get that the moles of solute equals 0.313656. Now our last relationship, our moles of solute times the molecular weight equals our grams of solute. So our molecular weight is just the grams, the 10.0, divided by our moles, which is 0.313656. And I'm guessing these are pretty cooked numbers. Yeah, those are pretty cooked numbers. So you get 32.01377. You've got 3 sig figs in all your answers, or all of the numbers that are given to you, so your molecular weight here is 32.0 grams per mole. It's going to follow a similar flow for osmotic pressure. If you're given the osmotic pressure pi, that equals TRIM, you're going to solve for the molarity, use the molarity to find the moles, and then use the moles and the mass of the solute given to get you back to the molecular weight. Now, a few points on molecular weights. Typically, they're going to be above 20. I say that to you because if you're getting something like 0.1, hydrogen weighs 1, so whatever molecular weight you're getting is less than the weight of hydrogen. Hydrogen gas itself weighs 2. So your lightest organic molecule is something like methanol. See here, 12 plus 16, 28. That's roughly 32 AMUs. So that's going to be the bottom end of your atomic weight, of your molecular weights for anything that would dissolve in water. And that was part of the reason I asked you that question in the discussion board last week about how would you take this information and to find molecular weight. Right, so we got another version from freezing point depression is 8.35, Van Hoff is 1, the solvent is benzene, mass is 0.2 kilograms. So what's the molecular weight of the unknown? So same format. Looks like it's going to make you do a little bit more work for this problem. So we get delta T equals K I M. So grams of solvent is 15.0 grams. And we've got 0.200 kilograms. You're given the delta T. Freezing point depression is 8.35. For benzene, Kf is 5.12. And I is given to you as 1.00. So first thing you need to do, solve for your unknown variable. So molality in this case is the 8.35 divided by these two numbers. So the molality in this case is 1.63. 0.859. We're trailing a bunch of numbers. Next step is you want to find the moles of solvent, moles of solute. So that's just molality here is moles over the kilograms of solvent. So we're just going to multiply this whole thing over. So m times the 0.2. That's not right. Oh, it is. 0.326. 172. So the last relationship here, the moles of solute times the molecular weight equals the grams of solute. So our molecular weight is just our grams, the 15.0, divided by the 0.326172. And when we work that out, I get 45.98802. 3 sig figs here, 3 sig figs here, 3 sig figs here. So your final answer here is going to be 46.0 grams per mole. Yeah, that's how you would work that problem. Solve for the molality, take the molality and solve for moles, take the moles, take the weight divided by the moles, and this will end up getting you the molecular weight. This is actually one of the labs you're going to do this week, which is the freezing point depression. Yeah, I'm going to really advocate, like, start using Excel. This is something that we would actually, if we were doing this seated, we have already had to talk about, particularly in the lab. I make students use Excel a lot. This is not to disparage calculators. It's just that I can't tell you the last time I owned a calculator. Really, Excel is the program you need to be working with. For tests, calculators are just fine, but it's a skill that's actually very valuable to learn. Excel, the nice thing about Excel, and I'll share that with you really quick. So I've got these calculations worked out. Let's say I made a mistake. Instead of the delta T being 8.35, it's actually 8.95. Well, I can just change that to 8.95 and it will automatically update my answer down the road. So Excel carries a lot more precision, and it's also going to help you kind of like pick up if you make a mistake. It makes it a lot easier to go back and correct any type of work. But yeah, you're kind of getting to a level of chemistry where I mean we use calculators on tests just for practical reasons. It just stops you from cheating more than anything else. But really, you need to be getting more comfortable with Excel. So the writing tutorial, you're not going to have any formal written lab reports. It's just not going to be practical for you this semester to do. So the writing tutorial I gave you, I honestly just did not feel like updating it for an online course. That's more what my CEDIC courses deal with. So the lab reports you're seeing on WebAssign, that's not what I traditionally call a lab report. What I call a lab report is an actual formally written introduction, methods, data, all that. We're not going to do that this semester, and the reason we're not going to do that is you don't have the ability to form lab groups. Quite frankly, your lab kits are also not really lab kits. You're not working with anything too terribly precise. So we're going to stick more to doing the WebAssign, but you're seeing what's kind of left over from what I make my seated students do. So don't worry about doing peer review. Don't worry about, you're not going to do a true formal written lab report this summer just for practical reasons. You don't really have labs that lend themselves to formal lab reports. Now, in terms of how to set up sheets in Excel, it's really your personal preference. I would recommend Microsoft actually has some very good tutorials on how to work with Excel and how to set things up. I have personal preferences on how I set up my Excel sheets, but again, it's kind of my neuroses that I've picked up over the years. But I would really recommend just Googling Microsoft Excel tutorials. And Microsoft has actually put together some really good presentations on how to set them up and how to work with them. More you would be doing this in the lab. In the lab, we would already have had the discussion about how I'm going to take your calculators away from you and you're going to do this all in Excel. Most of you kind of become converts by the end of the semester, like, man, Excel's so much more powerful. It's like, yeah, but you've never had a reason to use it before, so I totally understand. Yeah, Michaela, I really want, like in the summer, if we were doing a CETA course, we would definitely be doing true written lab reports. But again, you're kind of doing a take-home lab kit. It's really hard to get you to write a lab report when you said, oh, I used a medicine dropper, or I used a 2 decimal point precision scale. So I like you get the writing exposure, but again, it's just kind of a practical end of teaching online in the summer. Probably this fall, when we're still doing online, I'll make them do written lab reports as well, but between this being online with kind of lower weight labs and it also only being 8 weeks, I don't want to put you through that type of stress. There's too much going on right now to request that of you. It'd be different if I had 16 weeks, but 8 weeks plus online, plus lab kits that are showing up like a week or two late, I'm just not going to do that to y'all. By the way, fun fact, faculty have like their own threads that we do with each other. People taking Chem 1 this summer, Carolina Biological promised us they could get us all the lab kits we would need for the Chem 1 students. Then they turned around and said, no, we can't actually do it, even though we're like 2 weeks into the semester at this point. So those people taking Chemistry 1 right now may not be getting lab kits to do their summer lab sections. So the on hold at the bookstore means that the bookstore itself has run out of lab kits. They've run out of vouchers for the lab kits. We are not allowed to post to our website saying that you should definitely not be going to the bookstore. You should definitely be buying directly from Carolina Biological. The reason is that it makes it look like we're saying the bookstore is not that good. Shoot me an email and I will send you the link directly to Carolina Biological, and you can order the kit directly from them. But right now the bookstore has kind of run out of lab kits, and even then they don't send you a lab kit, they send you a voucher that you send to Carolina Biological, and then they send you the lab kit. And Michaela, actually last semester I gave my students lab reports I had to write in college, and I gave them the 40-page monstrosity I had to write for a junior lab. And yeah, I totally get writing lab reports. It's a valuable skill. Like, we need to be teaching it to you. Do take a look to that writing tutorial. I've developed that with a lot of other professors, so even though it may not be useful for this course this semester, it does kind of give you feedback on how to write lab reports. A lot of instructors kind of have different flavors on how they want to do that, and that's why that tutorial was generated, was simply because, yeah, we did have instructors saying one thing and then another instructor said something completely different. It's kind of meant to explain at least where we're all coming from. Yeah, again, shoot me an email about that lab kit, and I'll send you the link directly to Carolina Biological. We're required to post material pro bookstore, and emails, we don't necessarily have to do that. Yeah, most definitely, especially with lab kits being back ordered like 2 weeks. Because the first lab report you would have written this summer would have been for the freezing point depression lab. Most of you, there are several of you who don't even have kits for that. So not only would you be put at a disadvantage for being delayed, you would also like have to write your lab report after everyone else had. Traditionally, what I do in the summer is I give you 2 weeks to write the lab report. So you do the lab, you have 2 weeks to write it, and if you can look at the online lab reports, I do not believe in verbose lab reports. Like 5-6 pages is all I need. Just demonstrate that you understand what you did. That's the engineer in me coming out. But yeah, this summer that was entirely unrealistic. I do remember being a college student. All right, any other questions out there? All right, well, if y'all are good, I'll go ahead and sign off for today. Again, keep in mind we're going to do live streams 4 days a week. Please come with your questions. Please keep me informed. I'm using the discussion boards to see if there's any issues. I'm also using the feedback during this time and by email to see if there's any questions that are coming up. Don't forget your test is due Friday by midnight. Again, I'm going to look over them, so until you see that your work has been graded, don't worry about that grade. Worry about your grade after you see that you've gotten your work graded. Blackboard is notorious for just being completely wrong when it grades free responses, and that's roughly 80% of your test is the free responses. So again, usually with me, 24 hours to grade exams. If you take it Friday, I'm probably not going to get around to grading it until Monday, but again, with the exams, if you go look through your exams, if you think you did it right, send me an email, and I'll be in touch.